right, thanks for having me. Today, I want to show you some really, really cool robots that we developed at Romela, the Robotics and Mechanisms Laboratory at Virginia Tech. So the first robot I want to talk about is called Strider. It's a three-leg robot that is inspired by biology. But have you seen a nature that has 3 legs, animals? Probably not. I've seen a dog with, that's a different story, so I'm not going to go there. But before we talk about how it walks or why we're developing this 3-leg robot, let's look at pop culture. Like, for example, H.G. Wells' War of the Worlds, or this is a very popular video game called Half-Life, and they describe these like alien creatures that terrorize Earth. But our robot Strider does not walk like this, and there's a good reason why we're doing this. Now, if I click this clicker, it's going to show you a dynamic simulation animation of how this Strider is going to walk. Now, before I do that, when I go to conferences and I show this to my colleagues, everybody goes like, ooh, ah, this is so cool. So when I click this, everybody say, ooh, ah, okay? Ooh. Ah, isn't that cool? So what happens is, it flips its body 180 degrees, and this middle leg swings between 2 legs and catches the fall and stands up again. So the interesting thing is, it's not the traditional robots that you've seen that uses the motors to pick up your leg, but we're using the concept of passive dynamic locomotion. It's just swinging your leg. Like you're walking, you're not really using muscle to lift your leg and put your leg down like walking like a robot, but rather you're swinging it, catching the fall, store potential, and you walk like that. So it's inspired by how we humans walk, even though we have 2 legs. Now, we build many different types of, well, let me show you the next step. So eventually, we want to fold it up, shoot it up for long-range motion, and it deploys its legs almost like Star Wars. And with its long legs, it can absorb the shock when it lands, and then it can walk. By the way, it's very tall. So the thing that you see over here, the yellow thing, this is not a death ray. I want to tell you that for having cameras, for deploying sensors, because it's so tall, it's about 1.8 meters tall, it's good for seeing over bushes and those kind of things. So we built 3 prototypes so far. The one in the tall one is Strider 1. The problem is the body part was just too heavy. We had so many motors and gears to align things, so it didn't work. So we came up with an ingenious mechanical mechanism to get rid of the motors. So we got rid of all the motors, and instead of using mechatronics or electrical controls, we came up with a classic mechanical synthesis of a mechanism, and now with just one motor, we can align all the joints, and the top body is now light enough, so it's now taking steps in our lab. So this is the very first successful step, and it walks like that. So we still got a long way to go because it's passive. Whenever it hits the ground, it falls down. We also need to figure out how to make it stand up. Even standing up is very interesting. Normally, if you think, how would you make the stand up, you would think, oh, 3-leg push-ups. But besides that, you can do a twisting standing up to reduce the torque, or even a dynamic motion like this, like breakdancing. So there's a lot of interesting things we can do. Now, what's the next step? Now, at Virginia Tech, we have a pretty good football team. And during the halftime, of course, the band puts on a great show. And I've been always wanted to do a really, some kind of fun show during the halftime using our robots. But our robots are really small. So I was thinking, how can I make a really big robot that's going to carry the Virginia Tech flag and the hooky board? So hey, let's make a 10-meter tall, 3-story high version of Strider. And that's now a research project funded by DARPA called Taller, Tripedal Hyper-Altitudinal Leg Robot. So it's a 10-meter tall, 3-story high walking robot. Now, the reason why we're developing this, of course, it could be used for surveillance or a walking communication tower. But the really cool thing is we're really changing the paradigm of obstacle avoidance, change the paradigm of mobility. Now, obstacle avoidance is an important technology, especially for autonomous robots. So the robot needs to scan the environment and carefully plan how to avoid these obstacles. But if you have a 10-meter tall walking robot, you don't avoid obstacles, you step over them. Right? If there's a car, I don't care, I step over them. You can go across the water, or like chops can spear through a very highly densely vegetated area like a jungle. So that's what we're trying to do. We're in the beginning stages of the design of Taller. So hopefully next time I'll be able to show you a demonstration. This is another robot called Impass, Intelligent Mobility Platform and Actuated Spoke System. It's the best of both worlds of wheels and legs. Wheels are great. They're simple. I mean, we use wheels on our cars. But the problem is they're only good at relatively in a structured environment like the roads. Legs are great for unstructured environments, but they're just too complicated. So in this case, we have a rimless wheel or a spoked wheel. But the interesting thing is the spoke can move in and out of the hub. So in this video, it's trying to go over a very difficult terrain. In this case, it's a cushion. So whenever it touches the ground, the ground deforms. But it does have laser rangefinder sensors and cameras, but it's simply using the touch sensor on the foot to figure out reactively how to coordinate the motion. But the true beauty comes in when it encounters a very, very big obstacles. In this case, this box is more than 3 times of its nominal height. Then it switches to a deliberate mode using the laser rangefinder. It scans the shape and size of the obstacle, and it carefully coordinates the motion of the spokes. And it can climb over these kind of obstacles. So this can be used for search and rescue missions or for scientific exploration. And it can do a lot of other cool stuff too. All right, this robot is called Climber, Cable Suspended Limb Intelligent Matching Behavior Robot. A few years ago, I worked at NASA JPL. JPL is famous for the NASA, the Mars rovers. And I had a chance to really talk to, of course, the roboticists, but more with the geologists. And they always tell me that at Mars, the really exciting, the science-rich sites that they really want to visit is always on the cliffs. But these fantastic rovers cannot get on the cliffs. So I said, hey, let's try to develop a robot that can climb up and down cliffs. So inspired by how a person climbs a cliff with a cable, we designed Climber. So Climber, so as you can see here, it tries to figure out what's the best point to put its foot autonomously. Should I put it here, over there? Once it figures out what to put its foot, then in real time, it calculates the multi-force distribution, which means that how much force to exert to the surface so the body doesn't tip and the foot doesn't slip, friction constraint. And after it figures out where to put its foot, then with the force balance, it can lift the other foot. And there's a small winch, and it can pull itself up, and it can climb cliffs like this. Now, this robot is called MARS, Multi-Appendic Robotic System. It's based on the NASA JPL Lemur 2B robot. NASA is using this robot for in-space application that's going to walk outside the space station, but we're using this robot for other things. So it's an omnidirectional robot with some interesting payloads. Our students love to have fun. But we also use it for different things. How can it, multi-leg robot, walk on a very rough terrain using compliance or the springiness in its joints? Or this project is for the Navy, try to develop robots that can go on the coastal terrain where the sea meets the land. So in this case, difficult to see, but the sand has different moisture content, or the grain size is different. So the foot soil sinkage model changes. So it tries to adapt to the terrain to go over these very challenging terrain. Nowadays, we retired Mars, but Mars is now our receptionist. So if you have a chance to visit our lab at Virginia Tech, Mars comes out and says, hello, welcome to Virginia Tech, welcome to Rhode Island, and greets you. Just for fun. Oh, this is something very different. So this, we call it whole skin locomotion. So since I was a small kid, I've been fascinated by biology, especially single-celled organisms, and especially among them, the amoeba. So this is an actual movie clip of an amoeba. So how it moves, it oozes and morphs into different shapes. And I always wanted to make a robot that moves like that. You remember the Terminator 2, the liquid metal robot, right? So that's what I wanted to make. But it sounds almost ridiculous. It sounds almost impossible. So if you want to build a amoeba robot, what do you need to do? You need to study an amoeba. So we worked with biologists and tried to understand how an amoeba moves. And this is fascinating. So the process is called cytoplasmic streaming. So the inside is liquid called endoplasm. The outside skin is a gel-like skin called ectoplasm. So if the amoeba wants to move forward, the fluid flows forward, and something interesting happens at the head. The liquid transforms to the skin and builds the skin. But more interestingly, at the end, the skin liquefies and gets absorbed into the body. So in other words, a single particle, stationary until it reaches the end, liquefies, gets absorbed to the body, flows twice the velocity, and then it becomes a skin again. Isn't that fascinating? Biology. So that is called cytoplasmic streaming. So, okay, now we understand amoeba, how it moves, so let's build one. But how do you do that? So after month and month of brainstorming, our solution is rather simple. You actually probably have played with some of these. Does everybody recognize what that is? You can buy it at a toy store. It's called a water wiggler. It's a toy. It's like a elongated donut, filled, almost like a water balloon. So that's our solution, right? I mean, cheating. There's no liquid to gel to liquid transformation. True. However, if you think about it, the topology is the same thing. The outside skin goes inside and comes out again. So it's almost like a three-dimensional tank tread. So the application is, as you can see over here, the entire skin surface is used as a traction surface. So if it's touching the ground, it can go, obviously. If it's touching the ceiling or in a building collapses, we need to send in robots. This can squeeze between obstacles or medical applications like endoscopes. So it's going to be a very, very interesting locomotion mechanism for those kind of applications. Now, since this is a very different type of mechanism, we did not want to use your typical motors gears and pulleys, but come up with something very different. So we're using these actuation rings to make it go forward. In this case, we're storing potential energy into skin to make it go forward. Going backwards is film rewinding. But in this case, we're using active tension cords to go forward and backward, and we're measuring the efficiency and doing some study on the basic locomotion mechanisms. Besides elastic skin, we're also looking at rigid bodies. Like this is called a colloidal cycle. It's a 1 degree freedom everting mechanism, and we're figuring out how to synthesize the entire amoeba using these techniques. That yellow thing was actually the first working prototype. Does anybody recognize what that yellow thing is? You have it at home. Tape measure, right? I'm sure you played with it. When you bend the tape measure, it buckles. And if you do this, that bend moves around. You thought, well, this is fun, but you probably haven't thought beyond that. This is actually a very interesting mechanism. It's a traveling revolute joint. So if you buckle it once and buckle it once and you make it a loop, then without supporting anything in the middle, it holds its shape, just like a tank tread. So using property, using shape memory alloy to make it move. So if you have a hair dryer and heat one side, it moves a little bit. So that was our first prototype. So this is the freaky part. Now we worked with some researchers, scientists at University of Pennsylvania to make a chemically actuated version, and that's called Chimera. Isn't that cool? So it's now we're getting closer to the actual amoeba robot of my dream. This is another robot called Raphael, robotic air-powered hand with elastic ligaments. By the way, all our robots have cool acronyms. I learned that that's the best way to get funding from agencies, but this is the story. So there are fantastic robotic hands out there on the market today. The problem is they're just too expensive, tens of thousands of dollars. What we try to do here with this project is how can you make a ultra low-cost hand that is dexterous, yet strong enough to crush an empty soda can, yet can handle delicate objects like a raw egg or a light bulb. So our solution is not use motors, but use compressed air. Simply change the air pressure, you can change the force. So you can do force control and limited position control. So it's grabbing an egg, it can do many things. By the way, when the egg falls, we did catch that, so it didn't break. The best part of this, the first prototype, only $200 US to make. So you can think about the positive impact it can bring. This robot is called Hydras, Hyper Degrees of Freedom Robotic Articulated Serpentine. It's a family of snake robots, not for crawling on the ground, but it's for climbing structures. I talked to a lot of workers at the construction site, and every year, thousands of people, workers get killed or get injured by falling from scaffolding. So whenever there's dangerous situations, send in the robot. So this is a robot that can wrap itself up and converting the oscillating motion of the joints to a whole body rolling motion, so it can climb up structures. At the intersection, it can unwrap and transition to the other side. So this is Hydras. We had different versions of Hydras. Oh, this is a spin-off called Hydras Arm. The robot arm itself, though it looks cool, is nothing new. It's a 12 degrees of freedom serial chain. What is cool is the interface. That thing that one of my students are holding is a simply optical fiber cable. And first time using it, she's manipulating it like a pro because it simply mimics the shape of the optical fiber. So this is really interesting, and it's very important for teleoperation. Currently use these joysticks to manipulate these robotic arms. It's just too difficult to train and expensive. Something like this, so intuitive, you pick it up and you can start doing all these great stuff like picking up golf balls. All right, this robot is called Darwin. We have many, many different versions of Darwin. Again, dynamic anthropomorphic robot with intelligence. So we started this project long time ago in 2004. At the time, now these days you can actually buy these small robots on expensive like a hobby, but at this time this was very new. I was interested in human locomotion. I thought the best way to understand human walking probably is to build a humanoid robot and try to make it walk. So this was more of a feasibility study. What kind of actuators can you use? What kind of control system you use? So we didn't have any sensors. It's open loop. And as you probably know, this is what happens if you don't have any sensors. But based on that success in 2004, we designed the next generation Darwin 1 in 2005, and it can now stand up and walk. And this was very impressive at the time, 2005. But still notice that it has an umbilical cord. So we're still using off-board power and off-board computing. 2006, Darwin 2A was born. Now it's really time to have fun. Give it all the sensors it needs. Give all the computing equipment it needs. 1.5 gigahertz Pentium M chip, 2 FireWire cameras, inertial measurement units, force torque sensors on the foot, lithium polymer batteries, and now Darwin 2A is fully autonomous. Nobody's controlling anything, no remote controls, no power cords. It's looking around, searching the ball, and try to play a game of soccer. So it's looking around, searching for the goal. It found the ball. It tries to align, and it tries to kick, and Goal! So this was 3 a.m. in the morning on Saturday. Our students worked really, really hard. So why soccer? Now, there is a competition called Robocup. It's an international autonomous robot soccer competition with the official goal of by year 2050, 2050, we want to have a team of robots play soccer against the human World Cup champions and win. It is an official goal. It might sound ridiculous, but we believe that we can do it, and towards that, we're pushing the technology. So we've been participating since 2007. This was Darwin 3 in China 3 years ago. I think this was 3. This is 3 years ago in Germany. Oh, it was in Austria. So you can sort of. If you look carefully, they have a personality. I mean, if you look at the robot searching for the ball, look at his head, it's looking around. So it's actually a very, very exciting competition. So, by the way, in 2007, when he first participated, this is what I saw. This is the Louis Vuitton, everybody knows Louis Vuitton, Louis Vuitton Cup Baccarat Crystal Trophy. This is what you get if you win Robocup. And I saw it, and that was the most beautiful thing I've ever seen in my life, except for my wife. And I fell in love with it. And in this picture, I'm promising my students that we are going to win this and bring it to the United States. And this was in 2007. We'll get back to this. With Darwin, we do many things. For example, when the Roanoke Symphony Orchestra visited the campus, the guest conductor was Darwin. By the way, we cheated. It's not really conducting the orchestra. The orchestra is conducting the rover because it's simply hearing the beat and sort of dancing. But it's fun. This is the next generation Darwin 4. Now it's much more stronger, smarter, and macho. In this video, it's just showing off. I'm strong. I can do martial art movements. I can do Jackie Chan things and dynamic motions like kicking. It's pretty cool. And it walks away. So since then, we had something interesting happen. Since we published papers and a lot of demos, we're getting a lot of emails, phone calls from researchers from all around the world that they want to buy Darwin for research and education. The problem is, as a university, we couldn't really sell it, and it's just too expensive. So we wrote a research proposal to the National Science Foundation, NSF, and we proposed a Darwin OP. OP stands for Open Platform, and this Darwin is going to be not only low cost, you can also make it with minimal machining tools, and it is fully open source. Open source software, of course, but also open source hardware. All the CAD files, manuals of how to fabricate the parts, how to assemble it, everything you need to build this robot is online for free. And already people are using all around the world. About 400 units are being used worldwide now in less than a year. So now Darwin OP is open source. So researchers are using Darwin OP for many different research tasks. This is a group that's using Darwin OP for a new gripper. Interesting thing is it's not using another motor. It's using the other motors and using some clever cams and pulleys and springs to do that. This is some work we did with University of Pennsylvania. So this is actually very, very impressive. So when there's external disturbances, it knows how to balance itself using its arms or hip, or if it's really strong, it can use its foot, just like on the subway. You grab this and do this. So it does that by machine learning using artificial intelligence. Some other cool things that we do, making robot cooperate together, in this case, lifting a stretcher together. This is very, very difficult technology. So people around the world are using Darwin OP for high-end research and education outreach activities. Oh, by the way, all of our robot videos always end with the same thing, such as that, which shows that it's very difficult. This is the inside of Darwin OP's brain. You can see what it's seeing, how it interprets, and what it's doing. You can see what it's thinking. You can see the software inside. Now, I talked about Robocop as the goal is by the 2050 have humans against the robots. So we started working on adult-sized robots. So Charlie Cognitive Humanoid Autonomous Robot Learning Intelligence, is our first attempt. Charlie 2 is all designed and fabricated in our lab at Romella. This is our first walking test. It's very impressive. The first walking test is about 0.4 meters per second, very respectable. Omnidirectional walking, and it's fully autonomous using the camera. It knows how to interpret what it sees in the environment. Also, it's very, very good at disturbance rejection. So while it's walking, even though you push it, it knows how to balance. By the way, that's a baby shoe on the end of the stick. So you push it, it knows how to use its ankles. It has a sensor called an IMU, Inertial Measurement Unit. It's a balance sensor like your inner ear. So we use those to, when we do demos, I let people just push our robot and it knows how to balance. Okay, let's go back to, we're running out of time. I'm just going to talk about one thing. So let's go back to Robocup. So this picture actually captures the excitement of Robocup. That's me over there doing the fist pump, my students in airtime. Let me show you just quick clips of Robocup. So we entered in the adult size division with Charlie and the kid size division with Darwin. This is the adult size division. Look at its head. It's looking around, looking for the goal where the ball is, and it's trying to think. Now, the adult size is a little bit boring. It's 1 against 1. It needs to find the ball, dribble the ball to the other side, and then it can kick it. So it's looking around, searching for the goal. Again, nobody's controlling it. Everything is fully autonomous.
Charlie, you got this. Let's go, Hokies!
And now, the really interesting thing is, the really funny thing is, I mean, let's face it, the robot walks like this, and it kicks like this. But if you hear the cheering, we are so excited because we do know how difficult this really is. Let's quickly look at the kid-size division. Oh, this is an embarrassing scene. So I think this was against the Japanese team, and then we lost the goal. Okay. Another quick video, 30-second video of the actual game. It's sped up a little bit at the beginning. It's 3 against 3. They also do team play. It's pretty exciting. We have a big fan base, so if you can hear carefully, you can hear people chanting, Darwin. All right, lastly, so how did he do? You remember that photo in 2007 I showed you? I fell in love with this trophy, and I promised that we're going to bring it to the United States. Finally, in 2011, we won Robocup, and also won this year as well in Mexico City. Thank you. So we brought the trophy for the very first time to the United States. If you look at the side, we have these leather badges. So when you win this trophy, you don't take it forever. You have it for 1 year and you need to return to the Federation. And it says Japan, Germany. So the interesting thing is the first 6 years, Japan took it because they were the champions. And then Germany took it for 2 years. And this was the very first time that we captured it to the United States. And I would like to believe that this shows the shift in the humanoid robot superpower from Japan to Germany to the United States. Thank you. Skip all these things. One last very important message. So we already started our robot in the real soccer field. Everybody loves robot soccer, but a lot of people ask us, why are you spending so much time, energy, money in developing soccer-playing robots? Aren't there other more important things that you can do with robots? Yes. However, if you think about it, if a robot cannot even play a game of soccer, how would you use this for real-life situations? So we're doing that right now. All the technology developed for playing robot soccer, now we're using it to save people's lives. This is a Project Sapphire for the Navy. It's a firefighting robot for the Navy ships. And I'll leave it over there, and we're out of time. So thank you very much.